In this lesson, we're going to look at logarithmic functions in more depth than we did when we introduced it in 6.3. The thing we're going to look at here is graphing. All right, so we're going to graph y equals log base 2 of x. We're going to look at domain, range, x-intercept, and asymptote, and then what the end behavior of the graph is. One of the things we learned last lesson was that y equals log base 2 of x and y equals 2 to the power of x are inverses. So if I know how to graph y equals 2 to the power of x, the log function would just be the inverse. So I would take the x and y values and flip them. So y equals 2 to the power of x, if I make the exponent negative 2, it's 1/4. If it's negative 1, it's 1/2. If it's 0, it's 1. If it's 1, it's 2. If it's 2, it's 4, right? So that's what you're seeing there in red. That's the exponential function. The logarithmic function is each of those ordered pairs flipped for x and y. So same ordered pairs, just x is y, y is x now. That's what you're seeing in blue. If we're going to analyze domain, range, and all that stuff, well, first of all, domain, it starts at 0. Well, to the right of 0, right? It's never actually going to touch 0 because the asymptote's x equals 0. So the domain is x values greater than 0 because it's going to go to the right forever. Range is all real numbers. It's going down, it's going up. The x-intercept is at 1. There is no y-intercept for this one. End behaviors, as x approaches 0, so as x is going to the left, y is going to negative infinity, so it's going down. Right? As x approaches infinity, as x goes to the right, y approaches infinity, it's also going up. Right? So this is the complete inverse of that exponential function. All right, there's going to be 2 graphs to try it. So why don't you pause it here and then come back and check, and then we'll do the same thing for the second try it example. So I really just plotted 2 points here. When x is 0, the natural log of 0 is going to be 1, right? Because the exponent that you put on, when you put an exponent of 0 on e, you get 1, right? So when x is 1, the exponent you had to put on there to get it is 0. So that's what you're seeing there. The other point I plotted is I approximated an x value of e, so 2.718 approximately, so I try to put there. And that would get you an exponent of 1, right? Like the exponent you would put on e to get e is 1, so the y value would be 1 there. So that's the curve. Intercepts, there's an x-intercept at 1. Asymptote, it's a vertical asymptote at x equals 0, and then the end behavior is the same as the one we looked at in the previous example. As x approaches 0, y goes down forever, so negative infinity. As x approaches infinity to the right, y also approaches infinity. It's going to go up forever. All right, let's look at the second try it example. So pause it, figure it out, and then come back and compare answers. So in order to graph this one, you got a base of 1/2, right? So same deal. If you have an exponent of 0, it would equal 1. So x is 1, y is 0. You get that point there at 1, 0. The other point I can easily plot is when x is 1/2. That means the exponent was 1, right? The exponent you put on 1/2 to get 1/2 is 1. So the curve is going to look like that, right? Previous example, I didn't mention domain and range. Domains x greater than 0 and range is all real numbers for this example and the previous one, part A. Try it as well. Intercepts also the same. So you got an x-intercept at 1, asymptotes at x equals 0, and then the end behavior is the same as well. As x approaches 0 to the left, it's going up forever, so actually it should be positive infinity. And then as x approaches infinity, y is approaching negative infinity. All right, so let's take a look at example 2.